Hello everyone, let's get back to the lecture on mechanical behavior of materials. I'm Klaus-Dieter, course number 315008 in the spring semester 2022. And we are still talking dislocation theory. In the past I have introduced dislocations, simple dislocations, slip and so on. And today we want to talk about some special configurations. In particular, I like to concentrate on dislocations in face-center cubic closed-packed crystals. To resume, this is a FCC crystal where we have the 111 planes as shown here to the left. And if you look on top of the 111 plane, we now, if we introduce dislocations, then we have a Burgers vector. So we go from the position here B to B prime. But we also can go to that position B to C and C to B, which corresponds to a movement in 2 steps from B to B prime. So if I stack these layers now, I can stack a layer B on top of these gaps here of the layer A, called position B, and the next layer I can put then above A or above the position C. The 1 gives me stacking sequence of A, B, C, which is cubic. This is the FCC stacking sequence. And the other one, as we know already, has the stacking sequence A, B, A, B, A, B. And that would be a HCP structure. Now, let's put a dislocation in. We know in the cubic lattice on the 111 habit plane, we have the Burgers vector as shown there, A half minus 1, 1, 0. And that means putting one more plane in as shown by the gap here. So the above or below the drawing, we have one layer of atoms more roughly here than in the blue layer and towards U. So this would be a perfect dislocation. But now, instead of displacing by A half minus 1, 1, 0, we can also first displace at this dislocation line A6 and then minus 1, 2, minus 1, which is this little white arrow shown there. And that leads from the blue to the green stacking sequence. So we see we get a change of stacking sequence. And then we make it up in some other distance in the second dislocation line by A6 minus 2, 1, 1, given by that other little white arrow, and get back to the original stacking sequence ABC, ABC. So we have ABC here, and we have ABC there. But in the center here, we have a stacking fault. So we have a change, a local change of stacking sequence. So instead of having ABC, ABC, here with this dislocation, we call it a partial dislocation. We get AB, AB locally, and then we go further back to ABC, ABC. So this construct here from there to there, we call it an extended dislocation, which is defined or realized by 2 partial dislocations and a stacking fault. And these partial dislocations, we call them Shockley, after the physicist Shockley. So 2 partial dislocations and a stacking fault together make up one extended dislocation of a resulting Burgers vector A half minus 1, 1, 0. So the sum of these partial Burgers vector become the Burgers vector of the perfect dislocation. This is shown here in different diagrams as well. How this perfect dislocation in the first figure splits. So here we have still the perfect dislocation. We displace some of the atoms. For example, we displace this atom here. So then we get a situation as shown here. We would get a gap somewhere further away, and that's what's happening here. So we get two partials. We move these atoms, the atoms that would be originally here, 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 and there, and we move them by this partial dislocation Burgers vector. And then we can move the next row and the next row and the next row, so we get an extended dislocation as shown at the bottom figure. As we see here, we have the ABC, ABC, and eventually we have a AC, AC, and then we have ABC, ABC again. Or in another figure, we see there, again the situation is the same. We have a partial Burgers vector which goes with the down component, and when we have another partial Burgers vector which goes with the up component, and together they give the full dislocation vector. So let's look to the equilibrium when these partial dislocations with stacking fault would form, and what would be the spacing between them. So I call the spacing between them D, and of course we must balance the forces. We have an attractive force, namely the stacking fault energy per unit area, force number 1. That means I don't want to have a stacking fault. The stacking fault costs energy, and that would push the two dislocations together, the two partials together, in order to minimize the stacking fault energy. If there's no stacking fault, there's no cost of energy. But then we also know these partial dislocations, they have strain fields. They have stress and strain fields as shown in my last lesson. And let's treat them as partial screw dislocations. Then we know the force between them is G B to the squared divided by 4 pi, and the distance, which is D. Like equilibrium, of course, these two forces, they have to be the same, so they have to equilibrate, and then we can calculate the distance equals 4 pi gamma divided by shear modulus and the Burgers vector to the squared. So for copper, here's a numeric example. G is 48 gigapascal, gamma is 70 millijoule per square meter, and B is 0.26 nanometer, and that evaluates to a distance of 3.7 nanometer. So you see the distance here is well over 10 times the Burgers vector. It's a good spread of the dislocation. So in this figure again, we have AB representing a regular unextended dislocation, as we have treated them before, but then these regions BC and BD, they represent partial dislocations, so there and there. This regular unextended dislocation also can spread then into these two partials. And the region between the BC and the BD, so this shaded area, this darker gray shaded area, represents the stacking fault. In this region, the crystal has undergone intermediate slip, we say. Not full slip, but intermediate slip. BC and the stacking fault and BD, they represent the extended dislocation. So this is the extended dislocation here. The stacking fault together with these two dislocation lines. And the extended dislocations, in particular screw dislocations, define a specific slip plane. So you see, they work on a specific slip plane. They are all coplanar. Thus, extended screw dislocations can only cross-slip when the partial dislocation recombine. I point that out for screw dislocation because we know screw dislocation, they can cross-slip, not so for edge dislocations, but for screw dislocation we have this possibility of cross-slip. However, that only can happen when it recombines, and I come to that on the next page. And of course, the recombination requires some energy, because we just said before, we are in equilibrium of the distance d, the width d of this extended stacking fault, and to recombine it, I have to overcome some energy. So here it is illustrated, the cross slip. The cross slip for an extended dislocation. So far away from the plane where we want to cross slip. So let's say that's the line where we want to cross slip, where we have the intersecting planes and where it becomes more favorable from the Schmidt factor going from the one plane to the other plane. So let's say we start here with the extended dislocation, situation 1, and then we get recombination 2, and as this part is recombined, it can cross-slip. The recombined part can cross-slip, but of course I have to recombine the dislocation everywhere in order to cross, and then it can split again into two partials and stacking fault extended dislocation. Let's look more here to the stacking fault energy, which you can measure by knowing the shear modulus, Berger's vector, you know, B2, B3, divided by 2 pi and the distance of the dislocations. So usually B2 and B3, they may be the same or just opposite here, but same magnitude. And yeah, by observing these dislocations, which you do here in a transition electron image, microscope image of dissociated dislocations in zirconium nitride, in this example, showing visibility of stacking faults and partial dislocations. Reference is given there. So if we look to the energy and the width of dislocation, so the width is proportional to 1 over stacking fault energy, then we see the cross slip is more difficult in materials with low stacking fault energy, because with low stacking fault energy I have a wide width. Yeah, the D becomes large if gamma is small, and then it's more difficult to bring them together because they have this repulsive character. So high stacking fault energy materials will work harden more rapidly. So this is about work hardening. We will address this in more detail when we discuss work hardening. And here some numbers. So for stainless steel, stacking fault energy is low. It's smaller than 10 millijoule per square meter. It does also magnetic transformation because of the low stacking fault energy, but that's a different deformation mechanism. So low stacking fault energy, the fault width is here 0.45 nanometer, so 4.5 angstrom and the strain hardening rate is high. So cross slip is more difficult. For copper it's medium, so we compare it to copper, and aluminium it's high. Stacking fault energy 250 millijoule per square meter, so 25 times higher than for stainless steel. And the fault width therefore is narrow. Strain hardening rate is low, and the cross slip is easier. Here, if you look more into that paper which was illustrated there on the page before, again the two-beam transmission electron microscope of dislocated dissociations in zirconium nitride, and here again I repeat this a few lessons ago when we talked about characterization. Depending on the scattering vector of these dark field images, we see different contrasts. We see different contrasts because of this displacement vector of atoms with respect to the scattering vector. And from that you can work out the Burgers vectors and also the stacking fault sequence within these dislocations. So sometimes you don't see the stacking fault, you just see the dislocation lines, the partial dislocation lines, or surrounding of the partial dislocation lines. Yeah. Then you see only the stacking fault, you see both, and various observations. Here you only see one side, one of the partials. Yeah. Because these two partials, they are slightly inclined to each other. So if you choose a Burgers vector like G equals -202, anyway, this is just qualitatively that we can see them. Here we also see those kind of dislocations in the steel. So this is aluminium silicon 304 stainless steel. Also overlaps with the big twin boundary, but we see here dislocation which then splits into the extended dislocation, and maybe here splits again or recombines again into, there's a very faint line. Or here we see dislocation lines. Here we see a dislocation line, very nice. Of course it goes through, which then splits somehow into partials, and then recombines and splits again, as observed in these images. Again, for stacking fault energy, the energy just goes up as we have higher separation of partials, so we have larger area of stacking fault. So it just goes up with the area in between, while we now for dislocations, we have this repulsive energy. If we bring them close together, they repulse each other. We know this is a 1/r behavior if you're a little away from the core, and then it goes down, and eventually you equilibrate them, so the one is in equilibrium with the other. This is the minimum of this potential, the total energy. I like to introduce the Frank partial dislocations. They are in the following situation. I have my ABC here, and I have my ABC there, so ABC, ABC. And then I introduce a stacking fault just in some area, but now with a dislocation in this way, perpendicular. So this is a pyramidal dislocation loop. So of course this is a loop, yeah. It has either to touch the surface or it is a loop. So I insert this dislocation loop, and that you can see here in the observation, also TEM, prismatic and sessile dislocation loops in aluminium, 3.5% magnesium alloy quenched from 550. Right. So here we see the stripes, and the stripes, they are interference fringes of the stacking fault with the electron beam, while when it recovers into full dislocation loops, then these stripes would be gone, and you have a full dislocation loop. So you have various loops here. You have full dislocation loops and partial, frank partial dislocations. Frank was a researcher as well. And they can be sessile, because if you move them around along the prism, you would need too much energy. Another interesting aspect is the Cottrell-Lomé lock, or Lomé-Cottrell lock. You find both. So here the Cottrell-Lomé lock, where we have a dislocation on one plane, so on the 1, 1, minus 1 plane. So we have a full dislocation here, and we have a full dislocation there. Accordingly on the 1, 1, 1 plane, and they can split into partials. So two partials in the extended dislocation, they split as shown before, and eventually they move to each other, and then they interfere, they interact at the corner where the two planes, they meet together. So this situation is now a little bit emphasized. We have in the far field, let's say, the unsplit dislocation on the minus 111 plane and on the 111 plane, and then they split. They split as shown here. So we have a stacking fault surrounded by the two dislocations, 1/6 of minus 2, 1, 1, and 1/6 of minus 1, 2, 1. And then put them together, and they combine to 1/6, 0, 1, 1. And this 1/6, 0, 1, 1 would be on the habit plane 1, 0, 0, as I show on the next slide. So this is the cross section through the image in 2D. The A half 0, 0, 0, 1, 1 normal dislocation splits into these two partial dislocations, which are separated by the yellow line, and they move together. Similar on the other side, here we get those two partials, so A6, 2, minus 1, minus 1, and that A6, 2, minus 1, minus 1 combines with the A6, minus 1, 2, 1. So we have to add these two vectors up, this one and that one, gives the Newburger's vector added here together of A6, 1, 1, 0. But now the habit plane is a 0, 0, 1 plane. It's not the 1, 1, 1 plane. So the 0, 0, 1 plane is the plane that contains both B and the dislocation line, and this is not a slip plane. And therefore, the dislocation is sessile. We call this also a stair-rod dislocation. So then we have the situation of these stacking faults going onto two planes, going around the corner, with the sessile dislocation here. It cannot move. This one can move, but if this moves, then you change the energy. So if you probably want to sit in the typical equilibrium distance here, so this does not move far away, and the same this one on that side doesn't move. We talked about cross slip before. So this is a cross slip in a face-centered cubic crystal. We know we have the dislocation loop, and the dislocation loop may expand. and then it may expand in a way that it becomes more favorable by the Schmidt factor going onto one of the other planes. This is for screw dislocations, and eventually you have another cross slip to a parallel plane to the first plane. That introduces kinks and jogs. So here we have this kind of cross slip, which we call a jog. So if you have this zigzag, this is the Burgers vector, and along the Burgers vector we have this zigzag, and along the dislocation line goes up and then straight again. We call that a jog, and if it's in the same plane, we call it a kink. And accordingly, for the edge dislocation, we can have this zigzag in the plane. We call that a kink as well. And if it goes out of plane, this is kind of climb here, we call it a jog. So we see already, if this jog wants to move in this direction, if we want to move that jog towards us, then part of the dislocation needs to climb. And climbing in an edge dislocation costs energy. And not costs energy, costs mass transport, diffusion. So we have to add atoms there. If we add atoms here, a row of atoms and another row of atoms, then this edge moves, this jog moves towards us. And if we remove atoms, it moves into the other dimension, other direction. So that leads to the climb of dislocations. Climb of dislocation is where we have, for example, one dislocation here. You see here let's go around. 1, 2, 3, 4, 5 over. 1, 2, 3, 4, 5, 6, 7 down. 1, 2, 3, 4, 5 over. 1, 2, 3, 4, 5, 6, 7. No dislocation inside. Just a vacancy. But we see already, if we have a vacancy coming there, then we have already 2 atoms missing, and there can be more atoms missing. So eventually we can get an intrinsic dislocation loop. We have heard about vacancy diffusion in the diffusion course, so I won't go too much into detail here. But this movement of vacancies by diffusion is now important mechanism for the climb of dislocations. We start here and we see the dislocation is at this position where my mouse is, and now we get vacancies condensating at the dislocation, moving to the dislocation. Now the vacancy is there, and that's nothing else by moving the dislocation up 1, or with 2 vacancies, 2 lattice planes, lattice distances, perpendicular or with the perpendicular component to the habit plane. Now I like to introduce a different subject, namely the curvature of a dislocation, because we have the dislocation loops, and sometimes you have to bend the dislocation, and bending the dislocation costs some energy. We can say we have a line force gamma, which is kind of a surface tension force, and if you move this part of dislocation out here, then it costs energy because you make the line longer. So you need a specific shear stress to move this red dislocation from straight to the curvature, and you need to overcome the line force gamma and to maintain the radius of curvature r in a stable situation. And tau 0 is maximum when delta theta becomes 90 degrees. The outward force F out due to the applied stress, so here in the outward direction, is, we have had the forces before, tau 0 times b times dl per length unit, or dl unit, and this is 2 tau 0 r times d theta b, if this is d theta, if you look to the angle, and that's called the Peach-Köhler equation. Then the outward force is opposed by a line of tension force acting along OA. So we have a line tension force. If this gamma stretches and stretches here, then we get a force, a net force acting along AO, just stretching the line. And this F tension equals then 2 times gamma times sine d theta, you can work it out, which becomes then just the argument of the sine, 2 times gamma d theta for small values of theta. And of course the curvature will be maintained in equilibrium if the two forces are the same, and that sets 2 gamma d theta equals 2 tau 0 b r d theta, or resolves into tau 0 equals gamma over br, or we say a constant alpha times g b over r, where g is the shear modulus. So the line energy is the energy per length, has the same dimension as a force. It expresses a line tension, i.e. a force gamma, in the direction of the line vector, which tries to shorten the dislocation. Yeah, I make the line longer, then it costs some energy. Per length, it's the dimension of a force. That's how you can imagine it. And we set gamma equals alpha times g times b squared. So here are some curved dislocations. We know already dislocation loops. We have a straight line from A to B, a straight dislocation from A to B. There are two subjects, two precipitates, A and B, in the body, where you can which can pin a dislocation, or being the start and the end point of a dislocation. And then by putting a shear force on, we know the dislocation moves. Dislocation, let's say the shear force goes to the right, and it starts to yield and plastically deform. But because it's pinned at A and B, it has to bend. It's not moving straight, it has to bend. And here, upon further plastic deformation, it bends further, and then we know the edge character becomes a screw character when it bends to 90 degrees, which then moves in the other direction, perpendicular to the shear force, and eventually it expands in the backward shear direction, as discussed in the section about a full dislocation loop. So this is a part of the dislocation loop. Locally, we have this loop character, and of course, each part of the dislocations, you remember here's Burgers vector, or here we have introduction of a plane from the top, here the introduction of the plane from the bottom. So this is how it bends, and then it curls over. It curls over so far until these two parts, of course, they move now in this direction, and this part moves into that direction, and they can recombine to the situation that they split like this. And eventually this part moves in this direction, so it stretches, and that part moves in the opposite direction. This part moves in this direction. We have a dislocation loop now, the classical dislocation loop, which expands in all directions. And then when this line becomes straight, we start over with the top of the figure, A to B, and bend out again, curl around, recombine there where they touch, and have another loop. And that gives us, upon lot of shear, one loop, next loop, and a lot of concentric dislocation loops. That's shown a little bit here in the movie as well. This situation, so we have two pinning points, and then the bending and the curling, and the recombination there, where these two parts of the dislocation loop, the opposite parts, they meet. So it splits into two dislocation lines, and then it repeats again. We call that a Frank-Reed source of dislocations. It's a source of dislocations upon further plastic deformation. So this has been observed, a Frank-Reed source in silicon from this paper. Right, today is only the short lecture, so I like to emphasize on these special types of dislocations and dislocation loops. So we had the partial dislocations with the stacking fault, we had some logs, I briefly talked about kinks and jogs of dislocations, and then dislocation loop sources, which is the Frank source. With this in mind, I leave you, and next time I come to a new chapter on the dislocation theories though, which is the strengthening mechanisms of dislocations. In other words, work hardening. Have a good time. I think next week is Passover. We can meet in office hours if you like. Please send me an email. And see you again. Bye.